Now, to achieve these transfers and to achieve trust that these transfers has occurred, there's a few subtle problems that have to be solved, and they are not trivial at all. So first of all, recall that I talked about a blockchain being a network of computers. Now, we need to have a mechanism when you have a network of computers where information is stored at various locations so that we can agree that actually a transfer has occurred, right? So in other words, you may tell me that a transfer has occurred, but I need to trust that that has occurred, and then other people need to update the information too. So how is that happening? How do we generally achieve a consensus about something having occurred? Well, the basic way to explain this is to refer to as the Byzantine General, as the Byzantine's General problem. So there's a city which the Byzantine generals want to attack. And we start with a simple version where you have two generals. These generals are located on opposite sides of the city, so they cannot directly communicate with one another. Meaning that they can't communicate by waving at one another or talking to one another. And what they want to do is they want to attack the city. Now, their attack can only be successful if both of them attack simultaneously. If only one of them were to attack, not only would the attack fail, but also likely the army would be beaten and the entire siege would be over. So how can they achieve consensus about the date and time of an attack? Right. So now, of course, what the general could do, the one general that we have here on the right, he could send a messenger to the general on the left and say, we're going to attack at dawn tomorrow. And then the general on the right, on the left, receives this information, says, sure, that is good. And then he sends a messenger back to say, I agree, we attack at dawn. Now the question is, does the general on the right know that the general on the left has agreed to this? Well, he knows that he has agreed to it, but he does not know whether or not he will attack on the right. Why? Well, because the general on the left does not know whether or not the message has actually been received. So in order to remedy the situation, the general on the right would send another messenger back to say, I have received your message and I've received your confirmation of my message, so I agree that we will attack at dawn. And so then, will this general, however, attack at dawn? Well, he's still not sure, right? Because this confirmation message that he may have sent could have also been intercepted. So in order for that not to occur, the general on the left obviously would send another messenger back to say, I have received your confirmation of my confirmation, we're going to attack at dawn. And this goes back and forth and back and forth. And the question is, do they at any point in time agree that both of them know, so do they both have common knowledge they will attack, that the others, there's attack time will be at 9 o'clock the next morning? The answer to that is no. They can never achieve consensus here in this problem. So now that sucks. And in a bilateral system, that is actually a common problem. And not only has this been pointed out by the computer science literature, but also by the economics literature. So there is a paper by this electronic mail game by Arthur Rubinstein, a very famous paper on that one. Okay, now in some form, luckily, when we have a distributed system, we actually don't need everybody to agree at every given point in time. All that we need is that we have sufficiently many entities agree. Let me explain how that works. It's a little clever here. Suppose there is not just two generals, but there's many generals, and they also want to agree on this system. So they basically send the messages, they all want to agree on attack at the same time, or at least they need to have a sufficiently large crowd that would attack. So how could these guys achieve consensus? Now, the trick is that the proof of work protocol actually has this feature that it achieves consensus. Now let me explain the problem when you have a single general, which is like the proposer of a message, and he has this little army soldiers or captains that have to then initiate attack. So what needs to happen here is that sufficiently many entities would agree on something having occurred. So here's how it goes. The general sends messages to each of his captains. And then these captains communicate all with one another. And they send the message that they believe that they have received. So the general sends the attack times to each of his captains. And all of the captains send the information to one another. And then what each captain will do is, if the majority, or if a sufficiently large majority of messages that they have received says that they have to do one thing, then they will do whatever the majority says it should be done. That is the assumption of the decision rule. Okay, and so now, of course, if everybody is truthful, and a captain receives from the messenger, from the general, a particular message, and from all of the captains receives the message that they should all attack at dawn, they will all attack at dawn. Now, what happens, for instance, if there is a rogue, right? So here on the bottom right corner, there is a rogue captain. What will happen? Well, the general still sends the truthful message, and the captains that are truthful will all send truthful messages to one another. But the rogue guy sends a different message. Now, what do we have here in the situation? Well, you have the captain here in the corner receives 2 messages which say attack, and 1 message that says attack at some other, or do not attack. Right? Likewise, so what will he do? He will attack. What will the captain do that is a rogue, as in the middle here? Same situation. Now, what happens with the captain here on the right? Well, that captain has sent a faulty message. However, he still receives he has the consensus, as the majority of all decisions still say to attack, so he will also attack. And now when I say rogue, I want to be clear. It could be that this general or this captain sends out messages that are faulty through a faulty system, or the messages could have been intercepted, whatever it is. Right? So the important part is that this point here is a failure point. But that notwithstanding, given the protocol that they have, they would still have achieved system-wide consensus to attack at dawn. Okay? So the consensus is still reached. Now, what happens if the general, him or herself, is still rogue? So this general will send out 3 different messages, right, to each of these different soldiers, meaning that the generals in communications could have been intercepted. So what they will then do, they will send each the different messages to one another, and let's look at what they have in terms of the outcome, right? So they all have received 3 different pieces of information, right? And what happens here is, well, will they attack at dawn? No, they will not attack at dawn. So they still have a consensus reached, just the consensus is not to do anything, right? So the point here is that under certain circumstances, for the system, you can achieve consensus on what to do. Okay, so in the terms of the Byzantine General's problem, there is an equilibrium. If not too many of the nodes are compromised and faulty or rogue, and there is a precise mathematical formulation for that, they will receive consensus. And what the proof of work protocol in the blockchain does is essentially that it creates that consensus. So if you have these transactions, they are put into the mining protocol where they were these transactions were verified, and so the assumption here is that these signatures cannot be faked, and the miners have therefore created these blocks, right? Then the particular information processing power ensures that the different participants in the network will still agree that that something has happened. Now, how does this actually happen? And so this is a little bit subtle, but basically what occurs is as follows. The blockchain protocol needs a mechanism by which somebody who wants to produce a new block can prove that he or she actually has the ability to produce a new block. So the way it's done in the proof of work protocol is as follows: is you take the information of all these transactions, and then you produce a hash of that information, right? Now this hash is essentially is a digest, which means you take the information such as it is, and it's a digest which is unique to the information that comes. So all that it means basically is you take a large amount of text and you have a mathematical algorithm, and it creates an output text of a fixed length. Now, in order to prove that you are the one who can produce a new block, this output text has to have a specific form, which has to start with a certain number of zeros, right? Now, in order to find a hash of all this information with a number of zeros, you add an extra piece of information, which is this one that you see at the bottom here. It's called a nonce. And with the right information down here, the right nonce, the hash of the entire thing will start with a certain number of zeros. Okay, that sounds complex, but really what it is, it involves this nonce here. You have to randomly guess the right nonce, which creates a hash of the whole thing that starts with a number of zeros. So once you have found that nonce, you can distribute it to everybody else. Everybody will be able to see all the information. They can check what you've done by hashing the information that you get. And if they see that it starts with a certain number of zeros, they say, okay, this guy was allowed to do it, and therefore we accept this as truth. So that basically means that it's a Byzantine fault tolerant mechanism. Let me explain this again here. So, you have the miner, and the miner sends out this information. All of these guys can therefore check that information. They basically produce the hashes. They see that the hash of that information, the information being sent out, starts with the number of leading zeros. They transfer that to one another. Actually, they don't need to transfer that for one another, but they see that this is legitimate, and therefore they will accept this as truth. And that's the end.